Okay, so second order. It's the same as the first. Only thing is, let's see. I've got my problem here. The decomposition of HI is second order. Okay, so I should use the second order rate law. Second order with respect to HI, K equals 30 at 443 degrees Celsius. Okay, and that was 30 liters per mole minute. Write the rate equation. Rate equation is just that simple thing that's just rate equals K times concentration of your thing raised to whatever power, 2 in this case. I could put the K in, and I should make sure at some point on my test I show that I know that. 30 liters per mole minute times the concentration of HI squared, because it's second order. Okay, so how long? I'm looking for a time. How long will it take the concentration to drop from, so here's my initial concentration, 0.01, to 0.005 at 443 degrees. This, I only need it because my K is for that temperature, so this is the only temperature I have a K value for. If you change the temp, you change your K. K is a constant as long as temperature doesn't change. Okay, so I know that I'm going to use the second order. So I'm going to use this guy, 1 over concentration after time, minus 1 over the initial concentration equals negative, or equals KT. I'm going to let Chelsea in and she's just going to hang out. Hey, you can come in, but I'm taping, and you're going to be in the video now. Okay, cool. Chelsea just came in. Yeah. All right. So, how long will it take to go from this to this? I'll just use the second order equation. So that was 1 over the concentration after some time has gone by, minus 1 over what the initial concentration was. I'm pretty sure. I'm going to flip back and make sure that this is initial and that one's time. Yep. Okay, 1 over after some time minus 1 over the initial equals KT. Alright, so equals KT. So I'm looking for time. So I'm just going to rearrange this, divide both sides by K, right? So divide this by K, divide this by K, and I'm actually just going to plug in the K. Alright, and I can plug in my values. So my initial concentration was 0.01. The final concentration after time has gone by is 0.005. And my K is that 30 liters per mole minute. Okay. So, then I do this. I'm going to plug these guys in, and I'll get 200 minus 100 divided by 30. So 200 minus 100 is 100. 100 minus 30 is 3.3. And this is just T. So time equals 3.3. That's weird. Oh, shoot. Okay, 3.3. And then this is 1 over concentration, so that's moles per liter, right? But it's 1 divided by moles per liter, so it's really, you multiply by the reciprocal. This is really liters per mole in the top. So I have liters per mole, divided by liters per mole minute, Okay, and I know if I'm dividing by a fraction, I'm actually multiplying by the reciprocal. So I have 3.3 liters per mole times the reciprocal of this guy, moles, minute, liters. Okay, liters cancels out, moles cancels out, I'm left with minutes. 3.3 minutes. Okay, that's that. And I'll try one more. Oops. This guy, calculate the concentration of the HI after 12 minutes. So it's still a second order reaction. So I know I'm still going to use the second order integrated rate law. So 1 over the concentration after time has gone by minus 1 over concentration that you have initially equals the K constant times time. This time, the thing that I don't know is this, right? Because I have my initial concentration, it was given, 0.01. I know the K and I know the T. So I'm going to go ahead and actually just plug stuff in, and I'll solve for 1 over that final concentration. So 1 over concentration after some time, it's kind of like my 1 over x, is equal to, how about I'll add this to this side. So I have K was 30, and that was liters per mole minute. That was my K. times 12 minutes, right? Plus, I'm going to add this to both sides. 1 over 100th is going to be 100. So minus 100, so I'm going to go ahead and add 100 to both sides, so plus 100. Okay, so I've got plus 100 right there, and let's see, actually I have to type some stuff in. So I'll go 30 times 12, and I get 360 liters per mole minute times minute. Minutes crosses out, so I get 360 plus 100, so I get 460. And this was 1 over moles per liter, so it's liters per mole. Great, so I'm adding liters per mole, and I'm adding liters per mole. Liters per mole. So 460 liters per mole equals 1 over this concentration, right? Okay, so I'm going to go ahead and, let's say if I could multiply both sides by this unknown concentration and divide both sides by 460. So I'm going to kind of swap these. And that means 1 over 460 equals your final concentration after that amount of time. So 1 divided by 460. Okay, I get 0.00217, so 22, and that's going to be my molarity. Just to make sure it's right, I would plug it in and make sure that that minus that would equal